I've been dwelling on bell work, and I'm going to try something, and I think you guys might like it, but we'll see. All right, so here we go. You should see a wheel at the front, and on a daily basis, starting next class, I am going to spin the wheel on one of the bell work questions. One of your names is going to randomly pop up. If you can explain why the answer is what it is, not only get the answer right, but explain it, you'll get a point for your class. If your class gets 12 points, I'm going to bring you all donuts. So it's something you're going to work on a daily basis. As soon as your class reaches 12 points, you get donuts. Both the same thing's going to happen for you. The same thing's going to happen for A-level chemistry. We'll see who gets donuts first. Yes.
What type of donut?
Krispy Kreme. Krispy Kreme. So just a little added bonus to getting your bell works correctly. So I will try to be intentional with which bell work I select, that it's not like a crazy level 2, level 3 question, but at the same time, you need to be prepared for any type of question that comes your way. So this is just something to spice up the class a little bit. For those of you that were out last week, I know that there were some students that were out last week. I just wanted to remind you something of absences. First thing, if you are absent, you have to catch up with the notes, regardless of whether you're here or not. We're covering the standards, and this class stops for pretty much nothing, as anybody will tell you from the past. The only time that last year I had to not teach like the full class lesson was because all the juniors were out, and the juniors were more than half the class for like the college tour kind of deal. And so that ended up landing on the period we were at. So I had to like just do review exercises that day. But other than that, you see me here? We're continuing with what's going on. So we are on lesson 3, meaning that the first 2 lessons have been covered. That was a total of 18 things you need to know. Like if you add up all the individual standards, there's 18 things you need to know. And so if you missed either or both of those days, it is your responsibility to get caught up. I do also want to remind you that there is tutoring for your class specifically tomorrow. The next tutoring for your class specifically is tomorrow. If you need me to catch you up with anything, that would be the time to come to do so. I'm only doing tutoring for the ACE classes for now. Pre-ACE will be as their material gets a little bit more complicated. They're learning about significant figures at the moment. Yes?
Are you still doing the thing when you get like 5 extra credits?
Yes. Yep, that's the thing. You still get 5 extra credit points for coming to tutoring. So that was the one thing. I do record the lessons. I'm recording this lesson right now. So if you have to be excused early or you're not here at all, you can always go on Google Classroom and catch up. Just you will want to get the copy of the printed notes from me so you can fill in what you need to get all caught up. And so that was the one thing, was talking about absences and how you catch up. The next thing, bell work. So we're not going to spin today. I was just letting you know this is what it's going to look like. But next class, it will. The only time I'm going to excuse someone is if they're not present. So if someone's not present for a Tuesday class, and they come on Thursday, it would be cruel to spin their name when they might not have caught up with the lesson yet. So if it does, I'll just spin again, if that makes sense. Other than that, if you were here, then I'm going to call you potentially. Yes. I don't know. This is the first time see with this wheel. I don't know how this wheel works yet. Like, I don't know what this algorithm is. We'll learn as we go along. I'm still learning this board. So I think there's an option to like take your name out. And I've done that before. Like if you get spun a certain amount of times, take your name out. But we'll see how it goes. I don't have a for sure answer on that one yet. It just picks Justin every single time. Justin. All right, here we go. So let's go ahead and go over the bell work. I'm going to go ahead and answer today's bell work. I told you it's going to be next time. So starting next class, I'm going to choose one of the bell works, random name, which means during the bell work time, you need to definitely be working on the bell works. If you don't understand it, whoever's sitting at your table or whoever your friend is, if you have a friend in this class, see if they can explain it to you. Use that time wisely. Like I said, it's a minimum of 12 class periods, could be more. Get a dozen. I'll be buying donuts for the class if you get and can explain 12 different answers. All right, here we go. Which statement about electrons in a ground state carbon atom is correct? Let's see if you got it. So what first thing I would do, I guess, is think about its electron configuration. What is its electron configuration? Carbon has 6, so it's 1s, 2, 2s, 2, 2p, 2. Okay, with that, let's see if we can start analyzing. Are there 4 different energy levels?
No.
In order for there to be 4 different energy levels, you'd have to see a 1, a 2, a 3, and a 4 in front. Like 1 is 2, 2 all the way to 4 is 1. But that's not happening. So get out of here. That answer's irrelevant. Yes.
Mariani's going home.
Okay, bye. Don't forget your M&Ms. Second, are there more electrons contained in p orbitals than in s? Well, drawing out, we can see there's only 2 electrons in p orbitals where there's 4 in s. So, nah, get out of here with that. That's a silly answer as well. All right, C. The occupied orbital that has the highest energy is shaped like a sphere. Is that true?
No.
It's actually shaped like a dumbbell, right? Highest energy is always the last one. So it's got to be D. Like a process of elimination, it's got to be D. The answer is the occupied orbital of lowest energy is spherical. And if I was asking for you to explain why, you would say, well, the lowest energy is 1s, and s is shaped like a sphere. That's the reason why. And so the answer here is D. This is paper 1. Just as we were initially learning in the class in the early part, and even throughout the year, I like to designate which paper we're on. This was a paper 1 question. 1 mark. Probably towards the beginning of a test. This is usually around the beginning of the Cambridge exam. They go in order, typically. Not always, but typically. Let's take a look at the second one. You've been given a diagram. You were asked to do vanadium. So let's check to see if you got it right. Vanadium's 23. Vanadium has 23 electrons. So you start at the bottom. Used to be a song, I think Drake started from the bottom, now we're here. Don't know if any of you are Drake fans. But we're going to do 23. So we start at 1s. 2. Out of 23, I've used 2, so I'm at 21. Now I go to 2s and I do 2. That brings me to 19. In 2p, how many electrons do I fill?
6.
Is there an order?
Yes.
I did teach it last class. It's up, 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 then down, down, down. And I'll reteach that in a little bit. It's in today's notes. Up, 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 down, down, down. That's 6. So that brings me down to 13. 3s, how many? Every box always only gets 2. So 1, 2, 11. 3p, up, up, up. Just get in the habit of doing it. Down, down, down. 5 more. 4s, how many?
2.
2. And how do I fill the 3D?
Up, up, up.
Up, up, up. Up, up, up. Like that. Yes.
The S orbitals, is there a reason why we don't finish the arrows?
Oh, that's a me thing. You can write it as a full arrow. Should have done it the whole way. Here. Here. Like that. You
Oh, okay.
can go ahead and finish it.
That's the way you-
It's still correct. Yep. All right. It means positive and negative spin. You can do half arrows or full arrows. They're not really too picky on that. So that's the bell work. So on this bell work, if I had called you up for it, you would have literally just had to write it out. And if I knew that you did the 3 here and you would slide, you have to put 1 in each, you would have gotten the mark for your class, actually. So like I said, starting next class. Next class, work on your bell work hard. In that first 10 minutes of class, I'm calling someone. I don't know who. They'll be able to decide. All right, here we go. Today's lesson. And so you'll notice that you have some M&Ms. You have some Karsa, and you have a Sharpie. We'll be using that momentarily. At the end of the lesson, you're allowed to keep and eat your M&Ms, but don't eat them until you're done with what I'm going to be showing you in today's lesson, okay? All right, here we go. Learning objectives. Oh my gosh. Why are there so many? Good news and bad news. Bad news, there's so many. Good news, we're actually going to spend 2 class periods going over these objectives. I was looking at how long it took me last year to get through the material, and we definitely did not finish everything in one day. So it will be done between today and next class period, and that's fine. Before we go over learning objectives, let's talk about homework real quick. There's a homework that was due today. Let me be clear about the homework. I had written it on the first page, but I'm not sure if I didn't say it in words, so I'm going to tell you now. My preference is that you take a picture of your homework and you submit it online. That is the preference, and that you keep the paper. First of all, that allows me to be able to look at your work and grade it and give you feedback as a private comment on Google Classroom. So when you get feedback, you'll be able to look back at your paper and be like, oh, that's why that was right, that's why that was wrong, kind of deal. Whereas if you have it on paper, then you will have to wait to get your work back, and everybody turns in things at different times and it gets crazy. So make sure that you are turning in your work online. If you already turned in a physical paper, you can take it back. And even if it shows up late tonight, take a picture, upload it. I'm not going to take off any points. Remember, I always give you a 24-hour grace period anyways. I don't know if you remember, but I do give a 24-hour grace period for most assignments except for one. And I'll remind you of what that one is. So homework, that was due last night. If you turned it in on paper, but then you had to take it back to take the picture of it, and you turn it in tonight, am I going to count it late? I'm not going to count it late. I'm still going to give you up to full credit. If you get a question wrong, I will take off a little bit of points and give you the correction, just so you know. I won't take off a lot of points, but I will take off a little. So just so you're aware. So if you don't see you got 100, you should go back into the assignment and see what are the corrections that need to be made. I don't brutalize your grade, but it could go, if you get a lot wrong, it could go as low as 70 in the grade book, if that makes sense. But what you're really wanting to keep track of is the feedback. Now, I am going to tell you your first homework, I'm going to grade it over the weekend, and your second homework is due Monday night, so I'm going to grade that next week, Tuesday. So that way you know, and you'll see a private comment on Google Classroom if I had something to give you feedback on. It is important in this class that you are answering the questions, that you are trying the questions, and that when you're receiving feedback, that you're reading it and going back into your work and being like, oh, that makes sense, or ooh, I still don't understand that. Maybe I need to ask Ms. Leet in person and to see what's going on. All right, so that was homework. Homework, good. Next, if you weren't here last week, I went over schedule. This class moves fast, and this unit is short. This is the shortest unit of the class, meaning that you actually have a test coming up. It's now next week. So Unit 1 exam is next Thursday. And I double checked the date. I believe that's 0907 actually. That's when I see you all. Next Thursday is your Unit 1 exam. And so it's going to be about 30 marks, and you'll have half the class period to do it. It'll be a mix of multiple choice and written Cambridge questions. So you've got to get practice with the Cambridge questions. Next Thursday, first unit exam. Be prepared, study up for it. In the first part of class, I think I will go ahead because it is a shorter exam. Most of your exams will be full class period exams, but this is a shorter unit. So because of that, we should have time in the same day to review beforehand. So we should have some time to review. But last lesson of the unit is actually next class, which is the 31st. That's where we're going to end the standards for the first unit. So that means that next Tuesday, I'm actually going to start the next unit. Next Tuesday, I'm starting at the unit 2. This class is fast. I didn't want to give you a test right after Labor Day weekend. That's why we're going to have a lesson in between. I didn't think it would be nice for you to come off a 3-day weekend and have an exam right after. So it's going to be next Thursday. That also gives the time for an additional tutoring session if you want to do a exam review tutoring session next week. So that's the reasoning to have the Unit 1 exam next Thursday instead of next Tuesday, to build in some review time in between. Also, you should notice some assignments posted last night on Google Classroom. Let me explain those real quick. The written homework I'm passing out, like paper today for that. I just posted it in advance. You'll notice that it says it's due next Monday on Google Classroom. That's the one I'm going to grade on Tuesday. Quizzes. Quizzes paper 1. There's 2 of them because I had them broken up into 2 sections. Quizzes paper 1. This is due next Tuesday. These are all paper 1 questions like you saw in the first bell work. No late grades are accepted there. When it closes, it closes. It's a quiz, basically. It's your quiz grade. You have a week, but technically you have after the last lesson, which is next class, so you have like 5 days to do it. There's 34 questions altogether in the quizzes. They are curved. I wrote the curved grade in the second one in the grade book so you can see what the curve is. You get 2 attempts. So if on the first attempt you don't like the score you got, then you can do it again. You only get 2 attempts though on the paper 1 quiz. And that counts as your quiz grade. It's a practice paper 1 questions. It's a hard deadline. For those of you who weren't here, I'm repeating it. I said it last week. But for those of you who weren't here, the reason I'm repeating it is the reason I have to make it a hard deadline is because I'm going to give you the answers the next day. I'm giving everyone the answers to the quizzes the next day. You're going to get them to your email. So if it's due on Tuesday night, I'm emailing you on Wednesday the actual answers for the paper 1. You can use that to practice for the actual unit exam. And so that's just helpful in terms of how to practice for paper 1. All right, so that was some things you needed to know. We'll go over some additional things next class, but we got to jump into today's lesson. And like I said, we're busy today. If you look at this, there's so many. What did I say about easy standard? I mean, what did I say about if you see a lot of standards, it means that the content is easy. When you have 1 or 2 standards in a lesson, it's going to be a lot. Like that 1 or 2 standards will fill the time of 10 other standards. So just be aware of that. So let's take a look. First, for those of you who weren't here, I'm going to repeat this as well. What you should do at the beginning of every lesson is you should read through the standards to see what you're already comfortable with or aware of, and what you're like, I have no clue what this is. So put a check mark if you know what this is or you remember this, and put an X if you have no clue. First one says, state and explain the variations in atomic radius and ionic radius across a period and down a group. Radius is size. So atomic radius is size of an atom. Ionic radius is size of an ion. Do you remember the trend with the periodic table? Check mark yes, X absolutely not. So it's either check mark if you got it, X if you're like, nope, don't remember that one at all. And it's okay. We did go over it last year, but we'll go over it again. 1.3.9. This should be new for everybody, but who knows? Maybe you studied chemistry on your own and you know what a free radical is. Describe a free radical as a species with 1 or more unpaired electrons. Any idea of that? If you know that, check mark. If you're like, I have no clue what that is, I'm going to put an X because I didn't teach that yet. Definitely not taught in the previous class. Define and use the term first ionization energy. Ionization energy. Do you remember those words maybe? But maybe not exactly what it is? Do you remember ionization energy, or is it just like no clue? If you remember, put a check mark. If you don't remember, put an X. Honesty is the best policy. I'm not checking what you know and what you don't know. This is a self-reflection exercise. Understand that ionization energy is due to attraction between the nucleus and the outermost electron. Identify and explain trends in ionization energies. Notice I wrote Thursday because I did already break up the lesson, and that's going to be one of the things we cover on Thursday. Yes. Yeah, grab the orange pass. Do you know where it is? Go ahead. Explain the factors influencing ionization energy. That'll also be covered next class period. This is definitely new for everybody. Construct equations to represent ionization energy. Whenever you see equations in this class, this means a chemical equation where you have reactants and products. So a chemical equation for ionization energy. Definitely not a thing in pre-ACE that we go over. So I'm going to put X for this. We didn't do that, but if you know that, put a check mark. Identify and explain the variation in successive ionization energies. We also definitely did not do this in pre-ACE. Deduce the electron configurations of elements using ionization energy data. Nope, didn't do that in pre-ACE. And this is just a repeat. I don't know why that's okay. So some of this may be somewhat familiar, and we go over it, you're like, oh yeah, I remember that trend. Some of it will be brand new to you today. So most of this unit up until this point was some things we have went over in pre-ACE. Calculating protons, neutrons, electrons, doing electron configurations, knowing about orbitals. This is one of the first lessons that you're going to see some brand new information. Before we move into the lesson, I wanted to go over an idea called spin pair repulsion. And so if you recall last class, and it was in the bell work as well, I told you that you had to put electrons of equal energy. So electrons of equal energy go into separate orbitals, which is separate areas of space, separate orbitals if possible. And so the formal reason of why is because two electrons in the same orbital repel each other. That is what I said last class. It actually has a fancy name. It's called spin pair repulsion. The repulsion is minimized when electrons spin in opposite directions, which is why you see one electron going up and the other electron going down. That's what that means. The electrons are spinning in opposite directions, which minimizes the repulsion. They still repel each other, just not as much. The thing is that these two electrons still repel each other. So if electrons have the ability to go into separate orbitals, they will go into separate orbitals, which is why when you're filling electrons across the same energy section, so the same energy sublevel, you put one electron in each orbital before pairing up. Remember that, and you're going to want to maybe write this back out for yourself. S is always going to be one orbital. Whenever you see an S sublevel, so that means one box. P always is in a set of 3 orbitals. So when you're filling, it's going to be 3 boxes. And then you only have to go up to D. D is 5 orbitals, which is 5 boxes. So that's something to remember. I'm giving a little bit of time. And then you're going to see a paper 1 question that has a topic that I don't think I saw directly stated in the objective, but I go through all the paper 1 questions and find anything that I can that's relevant. And so this is relevant into the material. So I'm going to go ahead and teach you what do paired and unpaired electrons mean so that you can answer this type of paper 1 question. What do you think a paired electron is? Go ahead.
Electron that has like a pair in the same orbital.
Right. So paired electrons means that you've got 2 electrons in the orbital. Pair means there's 2, right? Like a pair of shoes. Whereas unpaired electrons is when you have a single electron that doesn't have a second electron in the orbital. And so you're going to want to write this down because there is a possibility to get a Cambridge question like this. Question says, in which pair of elements, atoms, ions, stuff, in which pair Does each species, that's chemist word for stuff. Or scientist word for stuff. So it's not the same as biology. In biology, when you hear species, you're like, oh, yeah, species, animal. It's not like that. When you see in the physical sciences the word species, it means it's some kind of thing. It could be an atom, an ion, molecule, whatever. We just didn't want to specify. So we either use species or we use substance, one of those two. So in which pair does each species have the same number of unpaired electrons? How would we figure that out? What do you think? Go ahead.
Like electron configuration.
Electron configuration. Let's use the shorthand because otherwise it get too crazy. All the inner electron levels should be filled. So same number of unpaired electrons, you can use the outermost energy level because all the earlier energy levels would be paired. So all you have to write is the outermost energy level. So let's use the shorthand configuration. Aluminum, what would that be? So for aluminum, it would be neon. Then it's 3s2, 3p1.
One.
Can you figure out how many unpaired electrons are there?
One.
So that's 1 unpaired. Okay. Cu2 plus. How dare they? Rude. Why am I saying that's rude? Why is copper rude? It's an exception. They put it as an exception in a 1-point question. How fun. All right, copper with a +2 charge. What would that be? Let's go start with argon, right? Argon. The original configuration for copper without the plus charge is actually 4s1, 3d10. But then you take away 2 electrons. Where do you take the electron away from first? 4s. So we're going to change that. We're going to take that out. And then this changes to 3d what? 9. Okay. How many unpaired electrons are here?
1.
You're all brilliant. If you didn't get that, just to be clear on why it's 1. Look at 3d9 again. A lot of you are able to visualize this, which is fantastic. Because you don't have to write it out. Me writing it out is just explaining what's going on. It's a multiple choice. So you get the right answer, you get the right answer. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1. Wait a second. The answer? I'm confident that's the answer. Do I need to solve everything else? Please don't. Gosh. You know you only get 1 hour and 15 minutes for 40 questions, right? So if you know, and that's where confidence comes into play though. If you know you're right, you don't keep going. When you don't know you're right, that's where it's like wishy-washy. But if you're confused on exactly what to do, you're like, I have no clue what to do, then what do you do with the question? You skip it and you go back later if you got the time. Some questions on a paper 1, you're going to read the question and be like, I know exactly what I'm going to do here. Some questions you're going to read them and be like, what are they even? What is this? What are they even with this? Just because that's the nature of Cambridge exams. So this one, if you knew what to do, you go for it, and then that's it. I guess we should try to prove one of the others just to see. Which one would you like to check? Just pick one. Nickel. Yes, nickel. Calcium and nickel 2 plus? Okay. So, oh boy, that's fun. Calcium and nickel 2 plus. Calcium ends where? 4s? 2. How many unpaired electrons?
0.
0, right? 0 unpaired. And let's take a look at nickel. Nickel 2 plus. First do regular nickel. What's regular nickel?
3d8. 4s2, 3d8.
4s2, 3d8. Okay. But nickel 2 plus means
Take away 2.
take away 2 electrons from the last energy level. That's the 4th one. Goodbye. So you just have 3d8. How many paired electrons are here? How many unpaired electrons are here?
0.
Is
No,
it-
2.
Always go back to this if you need to draw it out. There's 8 of them, right? 1, 2, 3, 4, 5, 6, 7, 8. 2. So you can see here that these two are not the same, so that's not the answer. The question asked, which pair does each species have the same amount of unpaired electrons, which happen to be the first option. Yes.
So how does copper being an exception change the?
It actually doesn't in copper 2+. It does in copper 1+. So in a way, they were kind that they gave you one that if you had written it wrong and then you took the 2 electrons away, it actually would have worked out to be the same thing.
Right, but
But if it was copper
being
plus
an
1,
exception, how does it change the electron configuration?
in regular copper, it would be 4s1 3d10. And the idea, that would be regular copper, 4s1 3d10. You basically steal one from the S to put into the D to fill the D, the earlier energy
That's
level.
for copper and which one?
It's for copper and chromium. That's the exception. All right, so we've learned paired and unpaired electrons. Next. So this is a strange standard to put into this unit. You're literally just going to learn this, and then you're not going to see it again until organic chemistry. When we learn organic chemistry, free radical reactions are actually quite an interesting reaction that occurs up at the top layers of the atmosphere. Also, it happens, some free radicals are in your body you might have heard of. They're not good for you. They can be cancer-causing agents. So what is a free radical? You're like, oh, what happened there? What is a free radical? The formal chemistry definition for a free radical is any species that has one or more, usually it's one, unpaired electron. And so this is an example of a free radical. A chlorine atom that is unbonded. If you have a chlorine atom that is not existing as Cl2, it's just chlorine with its 7 electrons. This is unstable. Why? Not full. And so what happens with free radicals is they react with anything they can. They are going to steal electrons wherever they can get them. And if that's from in your body to cause a chain reaction, which is cancer causing, that's what's going to happen. And so it also happens in the atmosphere, and it's the reason why the ozone layer got depleted from chemicals we were using is because of free radicals that entered the atmosphere and would react with the O3 in the atmosphere. And so they're unstable, and they react with anything they can to become stable. And what happens is when they become stable, they cause something else to become unstable. And so it just happens over and over and over and over again. And the word is they radicalize other substances. And so all you got to know at this point in the class is how to identify, how to write a free radical, which is basically just an atom that has unpaired electron. It could also be a molecule that has an unpaired electron. Notice here I did give a graphic. Places where free radicals are: inflammation, air pollution, smoking, definitely cancer causing. We know that it causes lung cancer. Radiation and UV light, actually, from the sun. So this is some sources of free radicals. You know that if you get too much exposure to the sun, that can cause skin cancer as you get older. That's from free radicals. All right, so unstable react with anything they can to become stable. I just wanted to show you one quick example. This is a question 2 on a paper 1, meaning it's coming from these earlier standards. Which of these species would then be classified as a free radical? Which one would be a free radical? Can you pick it up? Would helium be a free radical? Okay. That's a noble guess. That's chilling. That's as stable as it gets, right? So you can take that out. All right, What do we think? So we're looking for unpaired electron. Which of these substances has at least one unpaired electron? Go ahead.
Beryllium minus.
Beryllium minus. Because instead of 4 electrons, it actually has 5 electrons. Whether you write the electron configuration or you write the valence electrons around it, let's do the electron configuration. It would be 1s2, 2s2, and 2p1. That's unpaired. That's going to be the answer. You can verify the others. O2 minus, that's actually super stable. 1s2, 2s2, and
2p6.
2p6. That's just like what? Just like neon. That's what oxygen wants to be, just like neon. So that's totally stable. So that ain't the answer. And let's technically check zinc. So what's zinc? 4s2, 3d, 10. Any unpaired electrons here?
Nope.
Nope. Definitely that weird one. Be minus. That's the free radical here. So that's how this applies at this point. We're going to talk more about free radicals later on in the course when we get to organic chemistry, actually, and the actual mechanism of reaction of a free radical. So right now, it's just recognizing that it's some kind of species that has an unpaired electron. You can do this by looking at the electron configuration or just by even looking at the valence electrons. All right, I wanted to bring up, you don't need to memorize antioxidants, but antioxidants, if you've ever heard of them, anybody ever heard of it? Antioxidant, like blueberries, a lot of fruits that have vibrant colors are known to be antioxidants. And these are things that we eat, we have them in our diet because they actually negate the effects of free radicals. And so it's like anti-cancer. That's why you're supposed to eat a lot of these types of foods in your diet. And so if you look, there's red beans, wild blueberries, pinto beans, blueberries, cranberries, artichoke. I don't know if any of you like any of that, but these are foods that are high in antioxidants. So basically, they will donate electrons to the free radical to make it chill out. Hey, chill. Stop. And so that's what the antioxidant does, is it gives the unpaired electron species an additional electron. That's the purpose. So pretty cool. All right, so here we go into the hefty part of the lesson. We are going to look at trends for the size of an atom and then the size of an ion. And so periodic patterns and atomic radii. This is literally the same graph I gave in pre-ACE, for those of you who remember from pre-ACE chemistry. Knowing that the atomic size increases as we go down the period and as we go from left to right. In this class, not only do you need to know the trend, you will need to know the reason why. Lucky for you, the reason why for your periodic patterns are almost usually always the same. So whether you're explaining atomic radius or you're explaining ionization energy, the reasons are going to be extremely similar in how you write your answer. But so just remember the trend. The lower left-hand corner is the largest, triple L, meaning francium, biggest atom. And the smallest is at the top right-hand corner. So actually the smallest atom is helium. And so it goes smallest to largest. And so then we have to look at why. We're going to look at the reasons why down the group, and then we're going to look at the reasons why across a period. All right, you ready to start with your Sharpie and your paper? Go ahead and take your cardstock, okay? So for your cardstock, in the center of the paper, write one ring. One ring in the center of the paper. One ring. One small ring in the center of your paper. What is is a ring again from last class? What is that supposed to represent in the Bohr model?
Nucleus.
The energy level.
Energy level. So energy level. What elements have one energy level only?
Hydrogen.
Hydrogen and helium. So far, so good? Okay. Write a bigger ring. Write a second bigger ring outside the first ring. A bigger ring. Give yourself some space. A bigger ring outside the first ring. Question. What elements have two energy levels?
Lithium all the way to neon.
Lithium to neon, right? Write a third ring. Third ring, okay? Now we're talking sodium to argon. Question. Is hydrogen or is lithium or is sodium the biggest? Which one? Hydrogen, lithium, or sodium?
Sodium.
Why? Why? So it's got the biggest atomic size. Well, what's the definition of radius? Atomic radius. What's the definition of atomic size? What is atomic size? What's the size of the atom? What is it? Just the nucleus? Is the atom just the nucleus?
No.
No, it's mostly the electrons.
It's mostly empty space, right?
The electron cloud.
The electron cloud. So what atomic size is it's the distance from the nucleus to the
Electron.
which electrons?
The outer electron.
The outermost electrons, which is what we would call the valence shell. But we can just say outermost electrons just to prove a point. So why does sodium have the biggest atomic size and hydrogen would then have the smallest atomic size out of these three?
Because the distance is larger in sodium than in hydrogen.
Distance is greater because more energy levels, right? So it means the electron cloud is pretty much expanding. The space is expanding where electrons can be held. Okay. So it's explaining down the group. So then hopefully it makes sense. As they go down the group, the atoms get larger and larger and larger and larger and larger and larger. It's a trend. I see some writing, so I'm waiting. Put your pens down when you're done so I know to continue. Good? All right, so down a group. I wrote it. You wrote it yourself, but I wrote it here. The atomic radius increases down the group for a couple of reasons. The first one is down a group, each element has more shells of electrons, which is the same thing as saying a greater amount of energy levels filled with electrons. And this results in the valence electrons being farther from the nucleus. There's a second factor, actually, and this factor is called shielding. And I'm going to explain shielding more a little bit later, but the idea is that you've got, as you get a larger atom and you have more energy levels, there's more electrons that are in between the valence electrons and the nucleus in the middle. And those electrons shield the electrons on the outside from feeling the nucleus. So because there's a weaker attraction, because of the inner electrons blocking, the valence electrons get farther from the nucleus as a result because they're less, or they're more loosely held. They're more loosely held. And so across a period, across a period is the strange one. And we do have to explain it. So you'll notice I left this slide blank. I did that on purpose. We're going to use period 3 as an example. Sodium versus chlorine. Sodium versus chlorine. So sodium has how many energy levels?
3.
3. So it's got 3 energy levels. And how many protons does it have? 11 protons. Chlorine has how many energy levels? 3. How many protons does it have? 17 protons. The size of an atom is directly influenced by the attraction of the protons to the electrons. So the greater the attraction, the more the electrons are going to get closer and closer to the nucleus. So let's think about this. You've got sodium, it has positive 11 charge in the nucleus. And you've got chlorine has positive what charge in the nucleus?
17.
Positive 17. So do you think the electrons would be more strongly held to sodium or more strongly held to chlorine with the same amount of energy levels?
Chlorine.
Chlorine. The electrons are going to be more attracted to chlorine because it has a greater nuclear charge. So what is nuclear charge?
The charge in the nucleus.
It's basically the force exerted by the nucleus on electrons. Force exerted by the nucleus attracting electrons. So, with sodium, how many electrons are in the first energy level? You've got 2, right? How many are in the second?
8.
8 in the second energy level. 2 that are in S and 6 that are in P. So 8 altogether. And how many are in the third? For sodium though.
3.
2 plus 8 is 10.
Oh,
So just 1, right? And then chlorine, let's do the same exercise. How many electrons in the first? 2. How many in the second?
8.
8. How many in the third?
7.
7. So they've got the same amount of energy levels. So the question is, if this nucleus is more powerful, how does that affect the size? The electrons actually get closer. So across the period, size of atom decreases due to what reason specifically? Increased nuclear charge, which means more positive nucleus. It's the fancy wording for more positive nucleus, greater attraction, so it condenses, it constricts the atom due to greater nuclear charge. And in your response for Cambridge, you have to write that. You have to write greater nuclear charge, or you have to express what it is, the force of attraction between the protons in the nucleus and the electrons on the outside. You have to explain that. Alrighty, so that means that as I go across a period, the size gets smaller. As I go down, the size gets larger. That actually explains both trends. Now, are there a different amount of energy levels across a period? No. Are there a different amount of core electrons across a period?
Yes.
Core electrons means not valence. they would be the same, right? So what you also want to write, and sometimes there's a mark for this. If there's an additional mark, you would say that distance or amount of energy levels and core electrons, which we call that shielding, are insignificant factors. Across the period, you're only looking at the nuclear charge. You're not looking at the shielding of inner electrons. You're not looking at the amount of energy levels because the amount of energy levels are the same. So you only look at the nuclear charge. But down a group, you look at the amount of energy levels and you look at the core electrons are shielding the outer electrons. So it decreases their attraction, which means the size is larger. All right, so I'm gonna ask for you to turn your cardstock to the other side. Help you out this time. Turn the cardstock to the other side, and you should have 2 pieces of cardstock. This time you want to rate your energy levels large enough where M&Ms can fit. So like this. It doesn't have to be perfectly circular, but write your energy levels out, up to 4 energy levels, so 4 circles. Give yourself enough space that you'll be able to fit M&Ms. Got it? So something like this on your cardstock. 4. I'll give you some time. So 4. I'm not testing your ability to draw circles. A lot of brilliant students will get like a beaker and like different sizes of beakers and like use that to draw their circles. But just do your best. All right, the reason I'm going to bring this up is I'm going to explain to you the size of an atom versus the size of an ion. So size of an atom versus size of an ion. First of all, what's an ion again? We got to know this. So either electrons have been added
Or taken away.
have been added or taken away. Added if it's negative and taken away if it's positive. And so you have to know the size of an ion in comparison to the size of the atom it comes from. I did write in words here what's happening, but we're going to show it with the diagram. Negative ions are actually always going to be larger than the regular atom it comes from. Every time you add an electron, the size will actually get larger, and I'll explain why in a little bit. Positive ions will always be smaller than the regular atom. Let's see if we can justify this. So now, let's see. Let's look at magnesium. So, magnesium has 12 electrons and 12 protons as an atom. What I would like you to do is open your bag of M&Ms and see if you can fill your Bohr model with 12 electrons. Your Bohr model for magnesium. So open your bag of M&Ms, fill your Bohr model. How many electrons would you put in the first ring? How many would you put in the second ring? How many would you put in the third ring? I'm giving you some time to work it out. Yes. You have too many electrons in that first energy level. Too many. Too many, specifically. How many would you put in the first energy level? Many would you put in the second? How many would you put in the third? Yes. How many have? Perfect. I'm going to explain what to do next shortly.
We go straight.
Yes. Perfect. I'll explain what to do next shortly to visualize what's going on. How many for magnesium should you have in your second? Yes. Remember? You need a
Like at all.
And the third one has 2. Are you not paying attention? Here, look, have my 2. Have my 2.
Oh, no, that's fine. Homework 2, I'm passing out of the But technically, it's not going to be due until next week because I'm not
I
finishing
kind
the
of just
lesson.
feel all of yours on accident. I'm going to take the brown ones. I like brown. I know you like brown, so I'm going to take what you like.
Good? Good?
You can always just give me all the brown.
All right, so let me tell you what to do next. You don't have to write this good. You don't have to write this, but you should understand. How many protons are in the nucleus?
12.
12, right? Positive 12. What you should have written, if you've gotten it correct, is 2 electrons in the first energy level. You should have 8 in the second. And how many in the third? 2. Okay. So the first electron is actually harder to visualize than the second electron. Start by taking both electrons away. Magnesium going to magnesium plus 2. What do you observe happens when you take away the 2 electrons? Take them away. Bye. Oh my gosh, we lost the whole energy level, right? Positive ions are smaller. You agree? So when I did this, I got this now. And if an energy level is blank, that means it's not part of the distance. Because the distance is the distance between the nucleus and the outermost energy level that has an occupied electron. There has to be an electron in that energy level for it to count. So far, so good? So we know taking away electrons will decrease the size. And it will actually always decrease the size. So go back to regular magnesium, add the 2 electrons again. Add them back. Restore magnesium the general way. Regular magnesium. Now what if you made it magnesium plus 1? What would that look like? This is regular magnesium. What would magnesium plus 1 look like? So you would still have 2 electrons here. You would have 8 electrons here. And you would have how many electrons in your outside one? So the trend is when I take electrons away, each electron I take away actually decreases the size. Each electron taken decreases the size. It makes hopefully a whole lot of sense why taking 2 electrons away decreases the size a lot. But why would even taking 1 electron away decrease the size some? Can you reason out why that might be? So why? And I'm going to write this. Magnesium is greater in size than magnesium plus 1, which is greater in size than magnesium plus 2. Why is magnesium plus 1 smaller than regular magnesium? Is there a way we can justify that? Go ahead.
Well, if it's plus 1, it would have a smaller charge than the nucleus, right?
Right. So the electrons occupy a smaller overall charge than the nucleus, which means the nucleus has more power, right, in comparison to the electrons. And so if it has more force, it's going to gather its electrons. That's the idea. So the reason we would say is increased nuclear charge or increased force of the protons compared to the electrons. Increased nuclear charge, or another way we can say it is increased force of attraction of protons compared to electrons. So the protons hold on to their electrons better because they have overwhelming more positive charge than negative charge. You're going to want to write that in. By the way, take those 2 electrons off again. Take one and then take off the other. So for magnesium, take the 2 out again. Take them off. Take them off, right? You took that electron away from magnesium. What did you do to it? You ionized it, right? Do you think that takes some energy to steal an electron?
Yeah.
Like if the electrons are being held by the nucleus, do you think it might take some energy to steal an electron? That's part of the last part of the lesson. That's what ionization energy is, when you take that electron. We'll get to that in a little bit. All right, so we've taught now positive ions, which are always smaller than the atom they come from. And it's a trend. Every electron you take away will make the ion even smaller. So you could even gather that if you had a magnesium plus 3, it would be even smaller than magnesium plus 2.
Wait, but isn't argon smaller than chlorine?
For an atom. We're talking about ionic radius. That's an interesting question that we will get to because it's going to come up. So explaining ionic radii. Continue. Good? All right. What happens with the negative ion? So you can, I'm going to delete this. Are you okay with me deleting this? Because I got to rewrite on it. Wait. Let me see if I can just add another slide so I can save the notes. Duplicate. Insert. I'm trying to delete something. It's not letting me. Maybe if I go here. There we go. Delete. That way I could save it. All right, let's look at negative charge. Take a look at period 3 and pick your favorite non-metal in period 3. Has to be a non-metal. That is not argon, by the way. Okay, so phosphorus. Okay, we're gonna do phosphorus. So you're gonna get your M&Ms out again, and let's do the Bohr model for phosphorus. It's only got 3 more electrons than magnesium, so add 3 more.
She said do phosphorus.
Phosphorus.
So you add
That makes sense. This is how they would go. Orange one? Sure, give me brown.
Are we trading M&Ms?
Because I want it to be like,
The same color?
yeah.
Okay. Phosphorus. Yes? Currently has 15 protons and 15 electrons. Phosphorus atom. All right, we know phosphorus is a non-metal. What does that tell us about phosphorus? Does it want to gain or lose electrons? Gain. How many does it want to gain to become like its nearest noble gas?
3.
So to go to phosphorus ion, the way that it should be, it would be P3 minus, right? All right. So add three electrons. 3 M&Ms. Positive 15. And what happens when you fill the energy level? Protons filled in the nucleus that are attracting electrons. But how many electrons do you have now? 18, right? So the amount of energy levels is the same. Why? Because it said it in the rule. Why is P3 minus going to be larger? Because it is. It's going to be larger. What is our reasoning here? When we add electrons, why does that increase the size? So when you're looking at the comparison between the two, you've got positive 18 versus negative 18. So the nucleus still has the same pull it had before, but what's the problem? Go ahead.
I want to say because there's more negative charges, so it's going to repel more.
Right. So more negative charges in the electron cloud repel each other. And the idea is if, like, let's say we don't like each other, okay? Let's say we don't like each other. Do we want to be as close to each other as possible? Or if we could sit on the opposite side of the classroom or even get into a separate period, we may do that, right? So what happens to the electron cloud is it expands. Does that make sense? So because you have more electrons, but you have the same force of attraction in the center, this means that the actual size is going to increase. And this increases as you add every electron. So the trend is actually the same again. Going from phosphorus is actually going to be the smallest compared to P minus 1, which is going to be larger than P minus 2, which is going to be larger than, which is going to be smaller than P minus 3, where this is the largest, just to be clear, and this is the smallest. So as each electron is added, it makes the ion larger. So far, so good? So David brought up a point, and I do want to address it. What if you had this scenario? And it shows up on Cambridge questions, actually. So it's a good point to bring up. What if you had calcium plus 2, K plus 1, argon, Cl minus, I'm going to go crazy here, S2 minus, and P3 minus. Which would be the largest and which would be the smallest? How would you figure this out? So let's go ahead and map out in our head what's going on. Calcium has how many protons? Atomic number.
The one that's taking the most to travel back to a noble gas in charge. In the amount of electrons is going to be the smallest because it's more closely pulled by the protons.
I believe. This should say 18.
So if they stand in the same place but have more protons, the one with the most protons is going to be the one that's smaller?
Yes. Watch what I'm writing. You may want to just track it down, just because there's an explanation here, David. You're absolutely correct. These elements all have the same amount of electrons, don't they? Calcium plus 2, K plus 1, argon, chlorine minus 1, S2 minus, and P minus 3. They all have 18 electrons, like their nearest noble gas, or they are a noble gas, right? So Cambridge has asked this question before. Which of these would be largest, and which of these would be smallest? Well, you got to look at what's changing. What's changing? The charge of the nucleus, right? The proton charge, which is the force of the nucleus. This indicates the greatest force, because you've got the most protons there. And this is the weakest force. So what do you think in terms of size? What's the trend? This is going to be biggest because it's got the least attraction here. So biggest ionic radii. And this is the smallest ionic radii.
So first you focus on the electron charge, and then you focus on protons if they're in the same place.
Right. It's a lot of explaining, right? Just explain two simple trends. But in this class, you've got to understand the why. You can't just say what, that it increases or decreases. You have to explain why. And so the main ideas here have to do with forces of attraction between the nucleus and the electrons. That's what you have to use to explain. Alrighty. Giving you a little bit of time for those still writing, and then we'll continue. You are, well, let me see. Wait to eat your M&Ms yet. Wait for a little bit, just in case I have something else to explain to you. I know, it's like, they're right there. Am I good to move on?
Goes to a 18.
Well, yes and no. If I'm filling in order, it's 2, 8, 8, 2, and then these 10 are actually back in energy level 3, right? So when you're filling, it's 2, 8, 8, 2, and then you go back into energy level 3.
Okay.
All right, ionic radii trend. There's a trend, and it looks really awkward when you're looking across the periodic table. But one of you chose phosphorus, and then we had chosen magnesium. So across period 3, Na plus, Mg2 plus, Al plus 3, silicon 4 plus, P3 minus, S2 minus, Cl minus, argon. Take a look across the period. A lot of what Cambridge asks is looking at trends across the period. The radius from sodium to silicon gets smaller, 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 and then there's a gigantic jump. Why? What happens between silicon and phosphorus? Why is the size of phosphorus way bigger than the size of silicon? So in the movement from positive to negative, what does that actually mean?
One has a greater one.
How many electrons does silicon have with a +4 charge? Silicon has an atomic number 14, and a +4 charge means it has how many electrons? 10.
It goes from
That's because
to
the charge.
How
Okay,
many
so
electrons does phosphorus 3 minus have? Does this explain the difference in size between silicon and phosphorus?
silicon is trying to get towards neon, while silicon is trying to get towards argon,
Right.
which makes them go in the separate ways in
Right.
size.
So you may want to just write that little note there. The difference between silicon and phosphorus, even though they're literally sitting right next to each other on the periodic table, is silicon loses 4 electrons to become like neon and only has 2 energy levels, whereas phosphorus gains 3 electrons to become like argon and has 3 energy levels. So you get a gigantic jump between silicon and phosphorus in size because that's the difference in energy levels. And so the trend is sodium plus is bigger than Mg2 plus, which is bigger than Al plus 3, because remember, every electron you take away will actually decrease the size. And there's a greater nuclear charge as you're going across, greater positive charge.
Is it also true with nitrogen and oxygen and
Fluorine? Yeah.
cobalt?
Transition metals are strange. We don't talk about them. The only time we talk about transition metals is like in the very few exception, like with copper and chromium. In the A-level course, there's a whole chapter for transition metals. Yes. Yes. All right. Now that we have went through this thoroughly, see if you can answer these questions. Which is larger, Lithium atom or lithium ion? Which is larger? That's just what I'm going to ask. Which is larger? And you can circle the one. Positive ions are always smaller, right? So that's larger. Oxygen and its typical ion. What's oxygen's typical ion?
O2 plus,
Not 2 plus,
2 minus.
O2 minus, right? To get to its nearest noble gas has to gain 2. Which is larger, oxygen or oxygen 2 minus?
Oxygen 2 minus.
Correct. And nitride, what's its charge typically?
3 minus.
Versus fluorine, which is -1. And 3 minus versus fluorine 1 minus. I did teach this. Which one's larger? They've got the same total amount of electrons.
All right.
Back to this again. If they have the same amount of electrons, I'm asking which one's larger though.
Oh, nitride.
Nitride is larger.
That's crazy.
I'm asking which is larger. The one with the larger negative charge. The smaller one would be fluorine because it has more protons in comparison. Now Cambridge question time. Can we do this in a paper 1 question? You've got F minus, and E, and Na plus, to be clear. F minus versus Ne versus Na plus. Which order is from smallest to largest? You could take 2 answers out typically immediately.
It's the smallest.
Remember, positive charge means more attraction.
Yes, it's a noble gas. Noble gases are super small.
F minus means more, negative means more repulsion. So what's the order? Smallest to largest.
So it can't be B or D or C because of the.
And it can be A because sodium is also.
Right. So the sodium is bigger because it's on the 3rd level.
More repulsion means smaller or larger.
Oh, I get it. Okay, I get it.
Larger.
Because the F has less protons. Oh,
See, right? See, right? Yeah, that actually, I was
It's
looking.
not gonna happen.
I have the other one.
The order is the more positively charged one is always going to be the smallest because this indicates that the nucleus has a greater force of attraction, condensing, pulling the electrons in. Negative charge is going to be the largest when the amount of electrons are the same,
Oh,
always.
it's Ne.
And he's got to be in the middle, right? So you could have 50-50'd it.
Yeah.
Because Ne's got to be in the middle. All right, next topic. This one we are definitely not finishing today in terms of everything we got to know with ionization energy. I already organized the class in such a way to finish this next class, but we're going to get started with it. I brought up kind of what this is. If you've got your Bohr models, you can go ahead and create one for what element do you want to pick? Pick anything in period 3.
Aluminum.
You want to pick, that's not period 3.
Aluminum.
Anything in period 3. Did you say silicon? Okay, sure, silicon. So do silicon. Write your M&Ms in. How many M&Ms for silicon would go in energy level 1? M&Ms representing electrons. How many go in energy level 2? How many go in energy level 3? Two in energy level 1. 8 in energy level 2. And how many in energy level 3?
4.
Okay, hold on to that. Don't do anything with it yet. Just create silicon for now. The Bohr model for silicon. Actually, let me remember. I have some silicon hanging out somewhere. Let's see, I have a question. I'll see if I can pull out some silicon. Yes. You gotta have, 4 in the outermost. Good. Well, I mean, the electrons should spread apart because they repel each other, right?
Yeah.
So, but technically, if you wrote 284, it's correct. All right, so here we go. First things first. For silicon, take an electron away. Just take one. Take one away. Oh, did that take energy? Did you have to use energy to take that electron away?
Yes.
I mean, you moved your hand, didn't you? That was kinetic energy. Agree? First ionization energy. You have to memorize the definition. The formal definition, and this is something that I have often seen tested on a Cambridge exam, like 10 to 20% of the time. On a paper 2, I've seen this exact definition. So that means definitely memorize it, and it's quite possible I could put it on your first unit exam as part of your written questions. The first ionization energy is the energy needed to remove one electron from each atom when you have a mole of them. Oh boy, moles. So when you have a whole bunch of them, moles. In the gas state to form +1 ions. So you're going to want to underline this. Underline energy needed to remove one electron. And the second underline is each atom in a mole of atoms. And the third underline is gas state. This definition is worth 3 points when you see it typically. 1 point for each of those parts that I underlined. So if you forget gas state, 1 point's gone. If you forget the mole, 1 point's gone. If you just remember energy needed to remove an electron, you can guarantee yourself 1 out of 3. So this is a word for word definition. Gotta know it, memorize it, put it in your things I gotta know for the unit exam and revision for the end of year test. Now, take away another electron from silicon, second one. Would that be called the first ionization energy? It would be called what instead?
Second.
Perfect. So the second ionization energy would be taking away the?
Second electron.
Taking away the second electron. To form what charge? If I take away 2 electrons, it would be to form?
A positive 2 charge.
So that would be the key difference. So a third ionization energy would be taking away the?
Third electron.
How many ionization energies do you think silicon would typically have? Restore silicon. Restore silicon to its typical 14 electrons. How many electrons do you think you have to take away to get it to be like its nearest noble gas? From those 14 electrons, how many electrons do you take away? 4. So how many ionization energies do you think silicon typically has to form a compound?
4.
4. You have to remove 4 electrons. Every time you remove one, so remove all 4 now. 1, 2, 3, 4. Take them away. Every electron you remove requires some energy. For you, it's a little bit, oh no, don't eat the one you dropped on the floor. Actually, we're going to throw that up. Lost. Lost forever.
You lost an electron.
Lost forever. That electron is gone. Knocked out. That's actually, when we get to mass spectrometry craziness, mass spectrometry is knocking off electrons from atoms and molecules. So you literally did that. Anyways.
Is that in this year's curriculum?
It is at the end. It is in this year's curriculum at the end. All right, so what I've just illustrated, you actually have to know in equation form. Take a look at this. You have not seen this, well, except for in your Prius packet. all year. It's a reaction. And so you are going to have to, if you go back to the standards, you are going to have to write a reaction for the ionization energy of an element. And so let's take a look at what's written here. You've got regular calcium, okay? For the first ionization energy, what do? You take away one electron. So how do we write that in equation form? Calcium in the gas state. Remember, it's always gas phase only for ionization energy. So you got to write the state of matter. Calcium goes to calcium with a plus what charge? Do I have to write one? No, but we do. And then little g there. And then what happened to that electron? It's written on the side. So what you were doing with silicon, when you took away the electron, where'd you put it? You put it to the side, which is what's happening here. So the first ionization energy for calcium, you have to know how to create this equation, which I'm going to show you from scratch in a little bit. But the idea is that you write the element before you took the electron away, and then the ion after you took the electron away, and then you write the one electron on the side. I want you to notice something here. You have no idea what that means. But I'm going to give you a simple definition. Delta H, we're going to have a whole chapter on it later this year. But for now, you can think of it as just energy. Because remember, ionization energy is the amount of energy. 590 kJ. kJ stands for?
Kilojoules.
Kilojoules. Kilojoules are a different unit, but it's like calories. It's a source of energy. So this is saying to take the first electron away, it requires 590 kilojoules of energy for every mole. To take the second electron away for calcium, it takes 1,150 kilojoules for every mole. To take the third electron away from calcium, it takes 4,940. So what do you notice? There's a trend here. Every electron you take away does what? Requires more energy to take every electron away from its atom. Now, why do you think, and that's my question here. Do you have a question first?
Is it possible to take all electrons from an atom?
Yes.
What happens then?
You could have something like a calcium with a plus 20 charge, which is highly unstable and not existing on its own. But, you know, for pure science, people in the lab could be messing around with devices like mass spectrometers and applying tons of energy if they've got enough energy. If they've got a device with enough energy to make it happen, make it happen. So if it has an established value in the text, like if you look online and you look up 20th ionization energy of calcium and it exists, that means they've been able to do it.
Well, with all the things they did during the Cold War, I'm sure somebody had done it.
Has taken away 20 electrons from calcium. Now, how many electrons does calcium want to lose? How many?
2.
2. So to take the first electron takes 590. To take the second electron takes 1,150. To take the third electron takes 5,000. Why do you think the third ionization energy is so much larger? So they always increase, but notice the third ionization energy for energy is a lot greater. Why? Go ahead.
It's getting closer and closer to neutral charge.
Taking away 2 electrons
Well, it goes to the noble.
makes calcium like its nearest noble gas, right? Taking away 3 electrons would be equivalent or even worse than taking away an electron from a noble gas. Taking third electron is taking a core electron away, not a valence electron. So it's going to make something that's not stable. Calcium plus 3 is not stable. So calcium's good with losing 2 electrons, but it's not good with losing 3. And we learned that back in Prius when we know calcium's in group 2, loses 2 electrons, becomes like argon. Are we saying theoretically we could take a third? Sure. You got that much energy to put in, you could do it. Is it favorable? Absolutely not. So what we're going to do now is we're going to take a look at how to make equations from scratch. And yes, this does end up being a common question on paper 2. If you get ionization energy on paper 2, there is a decent chance that the next question would be similar to what you have. Not stable. Ready? Am I good to move on? So, something you gotta know. As you remove additional electrons from an atom to get the +1 charge, the +2 charge, the +3 charge, the +4 charge, it always requires more energy to remove additional electrons. And so what a successive ionization energy is to go from +1 to +2 to +3 to +4, so on and so forth. That's a successive ionization energy. And as you take additional electrons away, you need to recognize that the nucleus is getting more positive of a nuclear charge compared to the amount of electrons. The amount of protons is greater than the amount of electrons as you remove electrons away. And so the hold on existing electrons is stronger. So it requires more energy to take away the next electron. And so that's why in calcium you saw that the actual energy values were increasing. And then you're going to see a chart on the next page, and I don't want you to freak out at it. You should see it on your paper now. Don't freak out at that chart. It's a lot of numbers. Lots of numbers approaching. Ready to... Ah! Too many numbers. Okay. So when you're looking at successive ionization energies, you will actually be asked to figure out how many valence electrons an element has based on successive ionization energies. And so the idea is the following. Take a look at, let's go back to, let's go to phosphorus. How many valence electrons does phosphorus have? 5. Okay, so take a look at the numbers. Phosphorus, it's like this. It goes down the chart, just to interpret it properly. Phosphorus goes down the chart. To take away the first electron requires 1,000 of energy. The second electron requires 1,900. The third electron requires 2,900. The fourth requires 4,900. The fifth requires 6,000. And the sixth requires 21,000. Do you notice a big difference in any of these successive ionization energies? It's pointed out in yellow here. It's right here, right? From 6,000 to 21,000 is a way bigger difference than from 5,000 to 6,000. Would you agree? This is a difference of about 1,000. This is a difference of 15,000 to take the next electron. What does that mean?
They're taking away from another gas?
Right, equivalent to a core electron. So phosphorus, the way to think of it is phosphorus is okay with losing up to 5 electrons, but removing a sixth is pretty much, it's not impossible because there's a value, so it's been done, but it's very difficult. So take a look at another one. Take a look at magnesium. Magnesium, the first is 700, the second is 1,400, and they're pointing out to you the third one is 7,000, That's a way big difference between 1,000 to 7,000, 8,000. Why? Because magnesium is okay with losing how many electrons? 2. So removing the third would increase the ionization energy by a lot. So the biggest jump in ionization energy when removing electrons is always going to be, welcome back, where you find the valence electrons. So you're going to see a question, maybe in your homework, maybe in next class at the bell work, where you're given random values. Let's say you've got element X. And you've got successive ionization energy values. The first one is 500. The second one is 1,200. The third one is 12,000. The fourth one is 16,000. The fifth one is 22,000. My question, what group of the periodic table would element X be in? Kind of question you can get on a Cambridge exam. You've got element X. You've been given these successive ionization energies, 500, 1,200, 12,000, 16,000, 22,000. Where is the most likely group of the periodic table that element X is in? How would you figure that out?
By seeing where the farthest jump is.
Seeing where the biggest jump is. So where's the biggest jump? Go ahead.
Like between 4 and 5. So
Is
might
it?
be
No, it's between 2 and 3.
16,000 to 22,000 is a difference of 6,000.
No, that's 8,000.
Subtract them.
6,000.
It's 6,000.
Oh yes.
And for 2 and 3 is 10.
Between 2 and 3 is 10 times more, right? So where's the biggest jump?
From 2 and 3.
It's here. Is this enough information to tell me what group this is in? What group is this in? It's not necessarily magnesium, but it's group 2. Because the biggest jump is between 2 to 3.
That's great.
So that's the type of question you could see here with this standard. Biggest jump between 2 and 3. That tells me that this is group 2. Yes.
So if the biggest jump is between 1 and 2, it would be
1. So it's at the beginning of where the biggest jump is. And what that illustrates is that it's okay with losing that amount of electrons, but when I take the next one, it's like, no way. Lots of energy required to do that. Yes. You're right at the cutoff. Go ahead and run. All right, we're gonna go over one more slide before being done for the day. We're gonna check this. How do we write an equation to describe ionization energy? So this is the last thing I'm teaching for today. Yes. Then it's just practice questions. First ionization energy of calcium, how would we write an equation? It's literally the one example that's posted. So start with calcium and then write calcium losing how many electrons?
1.
Plus 1. What state of matter are all ionization energies taking place in?
Yes.
Gas. So you've got to remember that. That's actually part of the mark. And now you have taken an electron. Where do you put it? On the side. So that will give you a point if you were able to do that. That's it. That's 1 mark. A question like that is always 1 mark on a paper too. And do it for another scenario though. The third ionization energy of potassium. What does third ionization mean?
Sure.
Removing the third, which means how many have already been removed? 2. So where do we begin? K. But we have to write plus.
Plus 2.
No, we have to write
2.
gas.
Yeah, we do. Both of those are correct. But notice, if it's the third ionization energy, it means I'm going from 2 to 3. I've already removed 2, and I need to remove the third one. Now, Hakeem, you're absolutely correct. The next thing I need to incorporate is the state of matter. It is always something that takes place in the gas phase. This is measured in the gas phase. So you don't use standard states here. It's a specific process. It's in the gas phase. Now, where'd that electron go? Where is it? On the side. Always on the side. Because you're like, okay, well, it was pulled off. It's on the side. Add electron. Always one. All right, you try fifth ionization energy of sulfur. I'm going to talk up until when they call announcement. Just put the plus in between the gas and the E minus, and you got it. Correct. Correct. Yes. Oh, you can eat your M&Ms.
Go ahead.
Yes,
What do you want about?
I did not.
Money. You see that? It's not in my M&M.
I did not.
Good afternoon, Golden Lions. One quick reminder about mobile device distribution. Students, please make sure that your parents forward to me the copy of your receipt. Again, the receipt must be forwarded to me. Also, they have to do the mobile device agreement, which you all have that link in your email. If you have questions or concerns, please come see me before school or during lunch. Do not come down during class time. Thank you.
Good afternoon, Golden Lions. This is Emily, and these are your afternoon announcements.
Students, please remember to check your camera's email daily and report to school in proper CIE uniform. Make sure your elbow is solid white, black, or red and does not have large logos. If you are wearing crocs, you must wear the back strap. Also, please wear your student ID badge on your neck at all times. Chances will be issued to students who do not adhere to the uniform policy.
Please remember students are not allowed on the second floor or in the stairwells during lunch. Also, eating in the hallways is not permitted.
Enjoy your
Attention
M&Ms.
seniors, an important survey regarding grad batch was sent to your camera email. Please respond by Friday.
So that means
Last
three.
year's shirts are on sale on OSB. You will need a shirt if you plan on attending any field trips this year. You can also wear your spare shirts on Friday. Last day to purchase on OSB is September 17th. Please make sure to drop off your yellow sign activity form in the main office. These are due ASAP.
Please remember that you must wear your student ID every day. If you lost your ID, the cost for a replacement is $5. Art and Gardening Club is hosting a jeans day on Friday. Remember, torn or ripped jeans are not allowed. Cost to participate is $1. You can pay as you enter the building. This concludes our afternoon announcements.
All right,
Enjoy the rest of
before
your
you go, just a couple of things. The homework I'm passing out is due Monday night. You can start working through what you're comfortable with for anything that you don't recognize. Remember, I'm finishing this lesson next class. So, real quick, these last three exercises. This one right here will be the bell work next class. So I'm giving you a heads up. This is the bell work next class. I'm going to call someone. If you can explain it, you'll get your first point. So this one's going to be the bell work next class. There'll be another bell work question to accompany it, but this is the one I'm going to call. So be prepped for that.
And this would be great.
Yes. Good job. Good finish. The only thing left at the end is practice questions. You're done. Huh? That I'm good.
Are you proud of it?
You can throw it out. No homework. I don't want. The card stuff, you don't need to keep them. It's just to help you
Oh, I
understand.
really do.
Have fun with your M&Ms. You can eat them. I'll take the Sharpies. If you didn't get a homework paper from me, raise your hand. I think I gave one out to everyone, but just in case.
Thank you so much, Julia.
It's a gift, and I know how much you like
You got the homework?
Thank you so much. This really reflects me as a person. Thank you.
Hey, Vincent, I got one.
When is this?
For the homework, only do the questions you feel comfortable with. Otherwise, wait until the end of next lesson to finish the written homework. It's due Monday night, because we still have some topics to cover.
I didn't finish the last thing.
Oh, okay. okay. For me to sign off, give me a moment. Let me collect these first. I'm collecting your Sharpies or your M&Ms. Throw out your back.
You use one of these?
Each page.
I just use my I put my hand in, and whatever comes out is what I use.
Stripes you so well.
I think the thing is, I have a lot
Take a
more.
picture of it and upload it. The reason why
So you
so you can keep it for review. I don't want you to turn it in and then stop forever. That's the one from last time. Do now.
What do you mean?
Like upload it and turn it in. I said that you will have to tonight.
You read mine?
That's fine.
You just wrote it with it.
You ate mine. I did not eat yours. This last one. I did not eat yours, bro.
Yeah, you wrote it with it.
You must be hallucinating.
Your pencil box.
Huh?
Your pencil box.
Why?
Okay.
Just in case.
That looks like organic to me. That looks like organic to me.
Bro, David.
You won the little prize. Are you proud?
Concentration.
Where's my phone?
And
I don't know. You know, be careful. There's a lot of people taking stuff in the school. You gotta be careful.
have a good day, everybody.
Thank you, Damani. I'm like David.
See you
Put it
on
in my
the
pencil
next
box.
lesson of Unit 1.
I mean, do you have any fruit?
Right here.
But that's yours. That's not.
No, Damani can take mine away.
Bro, you eat my M&Ms. That's what you have to do. Why are you trying to? Why are you putting
Put that
the,
away, bro.
why you put the blame on me, bro? Hey, calm down, bro. I'll put it away. Where are you, bro? Like, how?
Yeah, go around. So you see,
Could you slow down?
you round in half, and you divide by the maximum.
This ain't you. This ain't you, good.
Then you divide by this, so they have to be
It's saying you, David. It's saying you.
Oh, yeah, it is.
basically.
I can tell you this.
So that's the addition. The whole, this, and this.
You know it's me.
But it's the same form. All three of these are the same form. Okay. These two are different forms. M1, D1, equals M2, D2. You may or may not remember this. It's called the dilution of solution. So if you have two concentrations and one volume, what you're supposed to do is these two go together. Okay. Oh. So it's 9.6 times 2 is 4. Okay. And then on the other side is the other molarity. And then you divide to solve for the other volume. Okay. This is the final solution. And then this is the initial. And how was that? Okay. That's the same there. That's topic 1. All right. Topic 2. Skeletal structuralist. So this goes from here. I remember learning about how to completely do it. Okay.
I'm gonna go this way.
Wait, hold on. That might be someone's though.
I hope paper.
Protein
Julio.
Gone.
is
I'm gonna wait for Alina.
so this has to have 1, 2, 3 carbons.
Serotonin.
On the second carbon, 1, 2, 3.
GABA.
You have what's called a methyl chain. Methyl is 1 carbon long. So on the second carbon, you've got another carbon coming out like that. Then you add hydrogens around until every carbon makes 4 bonds. Okay. So
Does
what
everyone
about
sharpen
for
that?
that means you've got OH on the second carbon. And I believe it'll tell you, it should say here for alcohol.
Oh.
Oh.
Okay.
It means you got an OH somewhere. Okay. So that's the idea there. And this tells you displayed what it looks like in skeletal, what it looks like. And there was one other thing to name.
Yeah.
So you have to know the functional group. This is carboxylic acid. And that is on that chart. So you have to identify the functional group first and then count the carbons. There's 2. The prefix for 2 is F, which is on here. F, prefix for 2. So it's S-anoic acid. It's carboxylic acid that has 2 So that's the idea. You have to basically look at the chart and use that to figure out, and then the amount of carbons is listed here. Okay, thank you. You're welcome. Okay, how may I help? Let me see. If not, I can pick it. I can get it for you another day because I'm not sure. I might have it.
Also the quizzes,
Yes.
I can do them.
Yes. You'll want to. I highly suggest waiting until the final lesson to do the quizzes. Like do it between Thursday and next week Tuesday. Because without learning the last lesson, the questions on the quizzes, I don't know if you remember, they're always scrambled.
Yeah.
So there's gonna be questions, it could be the first question that shows up, could be something we learn on Thursday. And I don't want you to just like guess, so it would be better if you wait. I have a copy here of the.
I was testing you to make sure that
I wait for you. Can you give me your trash?
Yes.
I almost dropped this water bottle. She showed us the shapes. The what?
Do you remember Leonie last year?
Prior, it's an SAS, yes.
For one of her classes, I would always look at it.
If you do it, so I had said you don't have to, but if you do it and you finish it, it's a plus 10% on one of the unit exams for this quarter. Okay?
Thank you.
She just got into the class, so I don't want to overwhelm you with stuff, but if you do it, it is a bonus.
Leonie for one of her classes needs a lab coat, and she was wondering if you'd be able to. I don't know. She asked me to ask you if I'm asking.
By when?
She didn't tell me. I can ask her now.
Yeah, ask her by when. I believe I have an extra at home. Do I give it to you?
117 is.
Is that the process here? I guess.
No.
108.
117 is the one with the horse.
No, horsey.
Like a Pokemon?
Yeah.
Oh, the Pokemon. Okay.
That's fine. I'm still recording, so anything that's been said.
By this Friday.
She needs it by Friday.